So, all right. So, good afternoon, ladies and gentlemen. I need to turn on the theme song for this class, and this is gonna be the sixth lecture of mathematical method for physics, and we are going to talk about what is called metrics today. Before I go into the material, I want to show you something new, which I did with the class website. If you go to our website, our new website, it has to spell VIEW, not the site as before. So go to this website. I have added the YouTube lecture videos on the website, like there. Okay, so now the video can be viewed on YouTube. So if you have friends, if you have friends maybe from other countries who would benefit from the English lecture, let them know. Okay, so we have a bigger class, we have more questions, and so it'll be more fun. Okay. So let's go to the material for today's lecture. Okay, dismiss, and then here we begin. And so we are going to talk about metrics, linear, inverse, and eigen, what they are, and I'm sure in a typical mathematical method for physics, we would spend a lot of time talking about the algorithm of how to compute the linear equation of a matrix, compute an inverse of a metric, and so on. Okay, and so but in this class we are going to do something different, and the reason is I think for introduction courses, it's not that important that you know the detail of how you would find the inverse of a matrix, for example, because you can always use software package to find an inverse or an eigen vector of a matrix. So that algorithms are not that important for introduction courses. What is more important that we are going to do today is to practice, to prepare your skills, to learn how to visualize problems in matrix form. And by using these 4 case studies, we are going to look at quantum mechanics of these very strange math properties of exponential function, and then try to do a homemade quadrature method and look at in quantum mechanics equation that we call Schrodinger equation, and then last optimization. And hopefully after you have been through all of these case studies, you gain skills of how to see problems in your research or in your work in the form of a matrix. Okay, so let's put that in Thai language a little bit. ในวิชาแมทเมธอดปกติที่เขาเรียนเขาก็จะใช้เวลาส่วนใหญ่ในการที่จะมาดูว่าอัลกอริทึมหรือกระบวนการในการที่จะแก้หา inverse ของ matrix หรือหา eigen vector matrix เนี่ยมีกระบวนการในการแก้ยังไงบ้างหายังไงบ้างนะครับแต่ว่าผมมองว่าไอกระบวนการในการหาเหล่านี้มันไม่ค่อยได้ถูกนำมาใช้มากนักอย่างน้อยๆก็เป็นในขั้นอินโทรของนักเรียนนะครับเพราะว่าส่วนใหญ่แล้วเราใช้แต่โปรแกรมและซอฟต์แวร์ในการที่จะหาค่าเหล่านี้นะครับยกเว้นแต่ว่าคุณเป็นนักวิจัยที่เจาะลึกจริงๆในการมาแก้สมการลิเนียร์ต้องการจะทำวิจัยให้มันแบบเร็วมากขึ้นแต่ว่าส่วนใหญ่แล้วเนี่ยเราไม่ค่อยได้มาเจาะลึกเพราะนั้นเนี่ยผมคิดว่ามีประโยชน์มากกว่าที่เราจะเอาเวลามาฝึกทักษะของคุณนะครับเพื่อจะให้คุณมีทักษะมากขึ้นในการมองโจทย์ต่างๆที่คุณต้องใช้ในงานวิจัยในงานของคุณเนี่ย มองให้กลายเป็นรูปแบบของเมทริกซ์แทนนะครับโดยที่เราจะมามีตัวอย่างในการที่จะศึกษา4โจทย์ด้วยกันเพื่อฝึกทักษะของคุณนะครับ and so let's get on with the next case study quantum mechanics the exponential function of a matrix okay before we go on with that let's go back with the basic of a matrix multiplication okay suppose we have a matrix like on the left here a very simple 3 by 3 matrix and we want to multiply a vector or in this case you can call it a 3 by 1 matrix multiply this green vector to the matrix so the way I would do that in my head I can visualize this multiplication by imagining that we rotate the vector around a little bit and then just cross multiply the numbers 2 times 1 0 times 2 and 1 times 2 then add them together you get 4 okay let's do it again for the next row 0 times 1 plus 3 times 2 and 0 times 2 you get 6 that's how I visualize the multiplication of the matrix okay now for the last row that's how we do it okay you tilt a little bit and you couple the numbers multiply them and add them together you get 5 in this case very simple okay just to get warmed up with the mathematics okay give me time to sip my coffee so let's go see example suppose I have the same matrix the same okay for the first second and third cases but I have 3 different vectors like in the first example I have this 1 2 2 and I go multiply them I get 4 6 5 as a result what if I have another vector like 1 1 half and 1 multiply them just imagine you take this out then you rotate the green vector and then couple with the matrix row by row you add them you get that result 3 3 half and 3 you have another example of the vector and that's the result of the multiplication 6 3 and 6 so if we combined all of these 3 examples in one shot in one single shot that's how we do it okay that is the first vector the light green one and that's the result and if we have 1 1 half 1 that's the middle example that's the result and lastly we have this dark green color you get that final answer for the this column of the matrix so that's how you multiply a matrix to a matrix you multiply vector by vector do it one by one you do the first column the second column and third column that's how you do the whole matrix and matrix multiplication okay so you get as a result 3 by 3 matrix in this case so how are you doing with the warming up of the basic of the multiplication now we have something rather perplexing and confusing to a lot of people. Suppose I have an exponential function. For example, I have e raised to the 2 power, e squared for short. What does e squared means? It means if you have the e, this 2.7 something, that's how I remember the e, okay? You multiply the e 2 times, you get that answer, 7.389. Now you have this guy, the thinking guy, the guy with a lot of tough question. So he would imagine, suppose we have a number, it's the same e number, but then raised to the power of a matrix. What would be the result? What would be the answer for this strange exercise? Sounds strange if you think about it, how would you find exponential function of a matrix อันนี้ก็เป็นกรณีพิเศษที่ถ้าเกิดว่าเรามีตัวเลขสักตัวหนึ่งนะครับเช่นเป็นตัว e นะครับแล้วก็มายกกำลัง2นี่แปลว่า e คูณกัน2ครั้งแต่ถ้าเป็นยกกำลังเมตริกซ์ขนาด2คูณ2นี่มันจะแปลว่าอะไรนะครับก็เราสามารถจะมานั่งวิเคราะห์กันนะครับคือการฝึกนะครับว่าคุณจะสามารถที่จะมองโจทย์ของคุณเนี่ยในรูปของเมตริกได้อย่างไรบ้างนะครับ I can make a comparison. I can imagine then what we have studied in the first day of this course. I remember that back maybe 5 weeks ago when I just beginning to meet my students. We have this expansion. We call that. So what is the name of this expansion? Can anyone tell me? There's a name for this expansion. Yes. I just put my question out there so I have time to enjoy my coffee. Anyone? Let's ask someone from who's very good at a math lab. Let's say Patrada. What is the name for this expansion?
Taylor expansion.
Very good. It's called Taylor expansion. We can always expand a simple function, a well-behaved function, into polynomial like this. And now I put the coefficients of the expansion in blue just to make it easier to see. Okay, it's a number. You get a number like 7.3 or something, just a number. Now we can visualize this problem in matrix form. And how do we do that? We can adapt. We can adapt this symbol. We can change from the x, which is a number, into a matrix A. Why do we do that? Because if we expand them into the right-hand side, we have a very simple matrix multiplication. For example, we have this a squared. It means a times a. What about this? A cubed. It means a times a times a, 3 times. What about a quadruple? It's a times a times a and times a 4 times. So we just keep the same coefficient, like this one is 1 over 2 factorials, same coefficients. But now we have a matrix instead. So let's do that. Let's try to do this adaptation of Taylor expansion. But in this case, in the form of a matrix multiplication instead. We have many terms like this I here, that is the identity matrix. What about A? A is that matrix here that this thinking guy is thinking about. At a squared, a cubed, and so forth. So let's do it term by term. That's my I matrix, a simple 2 by 2 identity matrix. What about, to make it simple to see the pattern of all of these complex exercises, let me put some color in the background of these matrices, okay? For I put this green color there. What about my A matrix? Also, I have this 0, 1, 1, 0, just like this guy is thinking about. Now I can put another color as the background of this matrix. Let's put it orange, like so. What about A squared? Well, we have A times A. Now when I do that, when I go back to the previous slides and do the same vector rotation and do the multiplication, here's what I got. By magic, I get back the I matrix, the same number with the I matrix. So that I put the green color there, okay, for this A squared. I get back identity matrix. What about A cubed? I do it 3 times. I go do it on my scratch paper, and I do it 3 times. Here's what I get. Oh, I get back the A matrix, like so. So I then put orange color here in this result. What about the A to the 4th power? 4 times 1, 2, 3, 4. I get back the green, which is the identity matrix. So we have, for each term, a pattern of green, orange, and so on. Okay, out sequences of alteration of these colors. So let's put all of this here back into the sum to get the final matrix. Well, the final result of the matrix, of course, it is a 2 by 2 matrix, and therefore you should have 4 elements. You have that upper left corner, you have each corner of this here. Let's look at first the upper left corner of this matrix, this corner here, okay? So we go back to the result that we have listed on the right hand of the slide and focus on the arrow here. The first one is the number 1, and then number 0, and then number 1 and number 0. That is the first element of all the terms. So I put them into the sum of this addition sign. I put them there like so, okay? Now don't forget that I need to put the coefficient in front of the result also. We have this here is 1, 0, 1, 0, and the coefficient also. So that's the upper left corner of the matrix. What about the down here? What should we get down here? The lower right corner. What should we get? Let's give you some time to think about it and notice the boxes.
is the same
The what?
เหมือนกับอันแรก
You said it correctly. Oh, okay. I am sorry. I forgot to give you the applauding okay, for the first answer for the Taylor expansion. And this one, what was the answer? For the lower right corner of the elements. You said what you said was correct. What was it? But I couldn't hear it very well because it's, speak louder.
อ๋อคำตอบเหมือนกับตัวแรกอะค่ะเพราะว่ามี
Very good. Okay. You got the same answer for the upper left. Okay, because for all the metrics here, you have the same number 1 1 0 0 1 1. So always the same number. Therefore, for this here, we have the same result for the lower right corner. What about the off diagonal? By the way, there is many technical terms for this matrix. This line here, we call this diagonal element, in this diagonal element. The other one, we call it off diagonal element of the matrix. For this, we have the same concept, but the 0 and 1s switch, okay? And therefore, we have instead begin with the 0 and then 1 and 0, so on. And this here, we have the same number as the other guy here. Okay, so it's very simple, and that will be the answer for the exponential function of a matrix, okay? But we can do a lot better here because we can kind of simplify it, make it much simpler form. Beginning with this here that we just got from the previous slide, and I can ask, can I make it shorter, make it small and compact to do? I can go back to the beginning of this course and look at all the list of the Taylor expansion function. And here's what I found on the internet. I found that if we have this here hyperbolic cosine function, we have that expansion. Okay, now that's very similar to what we have in the upper left corner. Begins with the 1, and that's the 1. It's the same. Now there's 0. Because we don't have the x order polynomial, we skip to the x squared right there, and then to the fourth power, so we have the same pattern. And therefore, if I just substitute x for what number, I get the exact same series as this upper left. So what number should we substitute x for? Which one? Any idea? I should substitute x for what number to get the exact same result as the upper left element of this matrix. Just to slow down a little bit, I still have half of my cup of coffee to go. Notice the blue color, blue color coefficient here, just to guide you through the pattern here. Yes. Oh, I seem to have this here. I can't hear very well from my students. Are you guys with me? Say something.
Yes,
Yes,
Oh, okay. All right. I just lure you into answering my question. Chanida, what should I put for x here to get the exact same result as this guy?
Is number 1.
X should be equal. Number 1, very good. So we have that cosine, hyperbolic cosine of 1, and that's the one. And the other one here is the same number. The next thing in the series is this sine function, psi h. And again, if I substitute 1 for x, I get this very compact answer of the result of the exponential function of there. So this thinking guy now become very happy. Now he knows how he can do that. A very strange property of mathematics. If you have a number which is an e and raise that number to a matrix, you get back a matrix with that form. Okay. Now, in general, you can have any A matrix. It can be some other number. It can be some strange number, and you're going to get back the matrix. Let's say B matrix. Okay. Now, I hope you have gained some little bit of skills of how you see these things, this math in matrix form. Okay, that's the key point of this lecture. Now, before we go on to the next topic, I have a homework for you guys. Okay. Now, this is very special properties of a matrix. If I instead change the problem from 0, 1, 1, 0 into something else, like I have 0 pi, minus pi, and 0, what would be the final answer for this here? Okay, so you can show me how to do it using numerical expansion. You add some number and you get some number and you tell me what it is, you get 2 points. Or you can prove using your scratch paper and pencils or a pen, and you get another 2 points. Okay, that's due a week from today. Okay, let's see what we get. I actually have the correct answer. The correct answer from Mr. Ron in Facebook. So what was your answer again? You there? Maybe we have lost him somehow. Okay. All right, that's fine. We don't want to give the solution away. Okay. Let's see. Now, let me shift the topic to another concept of the what we call a linear problem that we see every day in the in research. Suppose we have this here, a very simple multiplication of a matrix. We have that matrix and we want to multiply that number 1, 2, 2. What do we get? And this is a very easy problem. But suppose we ask in reverse. Suppose we know that the initial information of this problem is instead on the right-hand side of the multiplication. We have 4, 6, 5. Then we ask in reverse, what would be this vector? This is much more difficult to do. And we call that a linear problem. How do I get this? Okay, linear problem. And typically, we know the matrix M. We know the vector B on the right-hand side, and we want to find out, in this case, in this problem, what the X is. Okay. And like I said, when you have this linear problem, normally in your research, you don't go into the details of how you solve for X. You just call a function, you just use some of the subroutine from this software package, like Octave here, or you can use Excel's here even, or Wolfram Alpha and so on. Okay, so that's why I don't think it's a good idea for me to tell you the details of how you do that, but instead spend some time to practice how you would visualize your problem in the matrix form, and then use this software to do the task for you. Okay, the next one of the basic is what we call the inverse. Okay, suppose we have this bunch of matrix. We have 3 by 3, and then another one here. You want to know what is the result of this product here. That's an easy question. But suppose we do a reverse question here. We have instead the answer on the right, and we ask in reverse what would be that matrix. That is more difficult. We call that question an inverse problem. Okay, you want to find W. What is W instead? So that the right-hand side is 1, 1, 1, and 0. Now, before we go on to the next example of this linear and inverse problem, we have this one thing that's called the complexity of an operation, and that is for this problem of inverse or linear, it is usually n to the 3rd power. Okay, where n is the size of the matrix. What does that mean? It means you cannot just keep adding metric. You cannot just keep adding more the size of the matrix. Okay, why? Because usually the amount of your PC that you have goes linear. Okay, maybe you have in your lab you have 5 computers. Maybe next year you get 5 more, then you get another 5 more for the next year. But if the cost of calculation goes like n to the 3rd power, then it's much more time consuming to do this calculation. Okay. To actually practice how you would use that linear and inverse in your problem. So I have another exercise for you to practice. Okay, I can go back to the quadrature problem here that we have to do for the homework problem. In that problem, I have 5 points, and I want you to compute the integration of these 5 points using 3 methods. We have the trapezoidal, Simpsons, and then quadrature. Okay, do that for 3 of these function over here. Okay, now let's go see the solution before we practice doing what we call a homemade quadrature. So we are going to practice working on this one ourselves, and and then hopefully you gain some skills of how you deal with matrix and vector. Okay, let's go and see the solution of this homework problem. I can go back to let me see. I have this new activity here. Let me check if Ron actually answer. He cannot turn on the microphone right now. Okay, very good. Let me give you. Okay. Now, before I go on, and let's talk about this because this one has a lot of philosophical and many prospect in the research. Okay, so what is that I'm talking about here? The answer for this question, let's go back to the quizzes, the homework problem that I asked previously here. I asked you to compute what is the right hand side of this expression e to this strange 2 by 2 matrix. Now, Mr. Ron gave us the answer correctly in this message. He said it is minus I, okay, minus I, minus the identity matrix, okay. Now that is very similar to what we have in the math class. It's called Euler Identity. Okay, let me put that in Google just a little bit just to show you. You put that in Google and comes out, it's huge here. Yes, okay. So what is that? You even have this fancy, what's that? Let me look at this here. It's very interesting. You have this, wow, okay. So this girl must be, very in touch with the math. Okay. Now, suppose we have that identity, okay? E to the I, that I, so what is the I here in the typical Euler identity? Does anyone know? Just to get people to talk to me a little bit. What is the I here in Euler identity? What is that?
Is it imaginary part?
Very good. So we call that imaginary number, okay? So that if you sort of you get equal to -1 here, okay? So this Euler identity has the form like so because we are dealing with a complex number. This one, a complex number, you get equal to -1 on the right hand side, okay? If you go back to this homework problem, there is no complex number here. It's just simple real number, but in a matrix, in a 2 by 2 matrix. But you get almost the same pattern of the mathematics as Euler identity here. Now, why is that important? It's important because if you think about the big problem of the physics today, so what is that big problem? We want to combine quantum mechanics with gravity. Okay, that is the last frontier of the physics theory. You want to combine gravity with quantum mechanics. And that is not possible yet to do because quantum mechanics require complex number. And you cannot just put that easily into the formulation of gravity, okay? If you have this complex number, it's in gravity, you get strange properties. But what about this? What about this? in this identity, there is no complex number, just a real number in 2 by 2 matrix. Still, you get the same sort of pattern. So maybe there is a way to incorporate this identity and then combine that with the Einstein relativity equation, and you get quantum mechanics. Okay, let's put that in Thai because I want to inspire the young minds how you would do that ในโจทย์ใหญ่ๆของฟิสิกส์ที่เรากำลังศึกษาก็คือว่าเราจะใช้อะไรในการที่จะรวมเอาแรงโน้มถ่วงเข้ากับแรงของควอนตัมคือแรงที่เกี่ยวข้องกับแม่เหล็กไฟฟ้านิวเคลียร์ต่างๆอันนี้คือเป็นประเภทควอนตัมรวมเข้ามายังไงกับแรงโน้มถ่วงที่เป็นทฤษฎีของอัลเบิร์ตไอน์สไตน์นะครับอันนึงที่เป็นปัญหาก็คือว่าในแง่ของกลศาสตร์ควอนตัมเนี่ยเราต้องใช้เลขจำนวนจินตภาพหรือว่าเป็น complex number นะครับเพราะฉะนั้นเนี่ยมันก็จะออกมาในรูปแบบของเอกลักษณ์ออยเลอร์แบบนี้นะครับที่เราเห็นทั่วไปในสมการของกลศาสตร์ควอนตัมแต่ว่าถ้าเป็นสมการของไอน์สไตน์ที่เอามาใช้อธิบายแรงโน้มถ่วงเนี่ยมันไม่มี complex number แบบนั้นนะครับเพราะฉะนั้นเนี่ยมันก็จะเอามาใส่ได้ยากบางทีการที่เรามีเอกลักษณ์แบบนี้นะครับที่มีเฉพาะจำนวนจริงเท่านั้นอาจจะเป็นกระบวนการในการที่จะใส่เอกลักษณ์แบบนี้ใส่เข้าไปในสมการสนามโน้มถ่วงของไอน์สไตน์ทำให้เราได้โอกาสในการที่จะรวบรวมควอนตัมเข้ากับโน้มถ่วงได้นะครับในที่สุดแต่ผมไม่รู้นะครับอันนี้ผมก็เล่านิทานพูดไปเรื่อยเปื่อยนะครับตามประษาคนแก่นะครับก็หวังว่าคนหนุ่มๆสาวๆจะสามารถหาคำตอบนี้ได้ในอนาคตก่อนที่ผมจะตายไปนะครับโอเค and so with that notes, let's go back to what we have here. What was that? The homemade quadrature. Okay, so we have this homework problem that I want you to use that three methods, the trapezoidal, Simpsons, and then quadrature to compute the integration of these three functions. So what is that solution? You can go to our website and then click on this here, the integrations. Let me do that and show you a little bit about what you can do that, how you can do that. Okay, let's increase the font size so you can see it clearly. Okay, now numerical integration. Okay, we are going to evaluate this here. So what I do is that I choose the function so we have analytical answer for these because we want to check the accuracy of these answer. Okay, and I don't know, I just put that here in the Wolfram. I get the answer. Let me give you an example. I'm not that smart in doing these integration. I just simply check with the Wolfram. For example, I look at this first function. I put that in my Wolfram alpha, and then I get that solution. There you go. Very simple. Then I just copy that answer back into my notebook, like so. Okay. So how you do it? So let's do it with Python code. So we have 5 points, and in here I have to define the sampling points. Define my sampling points. So I have 5 points, and therefore the x location will be -1, -0.5, and so on. And then I have to compute this here. The sampling point for quadrature is not evenly spaced. It has some strange formula. I can go look online and see, let's see, Gauss quadrature, and I can check with the 5-point Gauss quadrature and look at the formula of the x position, or The technical term for that x position is what? Does anyone remember? The technical term for that location of the x. What do we call that? There's a name for that. The x. We call that, someone must remember that. It's in the third or maybe the fourth lecture. The W is the weights. The X, remember I put that in the Google speech to have it pronounced for us. What is it called?
Abscissus, something.
Abscissus, right? Very good. Abscissus. Abscissus. If you put in Thai, I mean I'm not making it up. If you put in Thai language, it's Google say abscissus. Let's try it again. Very okay. Abscissus. Abscissus. Quadrature. Quadrature. Very good. Okay. There you go. If I copy that, you know, I'm not making this up. I am trying to Google Translate. Okay, if I put that here, and it's in English, where's my E here? And I want it abscissus. Abscissus. Now, if I do that in Thai, and I want to know what Google would pronounce in Thai. Abscissus. Abscissus. Very nice. Okay, abscissus. Here I have to look at this abscissus from Wikipedia. So for 5 points, I have that abscissus location here, 1 plus there and so on, and I just put that here in my formula in Python, and then I go on computing the weights, okay, in which we learned how to do that from the previous class. What about the weight for quadrature? Again, I go back here and I look at the formula for these here, 3, 22, and so on. I just copy that value and put it back here, like so, okay, for the quadrature. Now we have the abscissus and the weight defined. Let me click on that to execute the program to see what we get. It's going to take some time for me for the Google to do its magic. Let's see, connected, very good. And now we have that done. So let's do the integration, okay? There you go. Now, there you go. I have this Python code to print out the value here of the exact answer and the value from each method, okay? And then the error. Now you see this here. If you look at this pattern, you see that trapezoidal is not so good. It's good, but it's not that good compared to other methods. You know, the error is huge compared to Simpsons. What about quadrature? Wow, very small. Okay, how's that? 8 zeros. 0.00000006. Okay, that's very small error for quadrature. If I do all of that function and then I put the answer in a very nice table just to show you the summary of the error for these methods. Here's what I found. I found that usually the Simpsons is always better. The error is always smaller than the trapezoidal here. That is smaller than that. And also quadrature is also very small compared to the rest of here. But look at this strange behavior. If you have a polynomial, like 5x to the 4th power, that's polynomial, or I3 is polynomial. This one, quadrature, gives the exact answer. Very strange, almost exact. Okay, that's like 0. That's like 0 error. Why is that? It's very strange. Why is that? That is the property of the quadrature. Okay, if the function that we are integrating is a polynomial up to a certain order, you get the perfect answer, like by magic. Okay, now we are going to do that ourselves to practice how we can use matrix and vector to solve problems. Again, it's not that important for you to look at the details, but the skills is much more important. The skills of how you visualize things in terms of matrix and vector. So let's do our homemade quadrature. This is called the Gauss quadrature, but let's do our own quadrature. Let's go back to the summary of these methods. Again, it is very amazing how we only have 5 points total, only 5 points for all 3 methods, trapezoidal, Simpsons, and quadrature. Same computing power for both 3, but we have much better accuracy. From here to the middle one, you get 10 times better. What about quadrature? You have 100,000 times better. That's amazing accuracy. 100,000 times better than trapezoidal. How is it even possible? Okay, so I dig up the history of these methods. Here's what I found. The trapezoidal method went back to the ancient Babylonian. Okay, that's like many thousand years ago. Okay, they already know how to do this integration using the area of below the curve. It's very amazing. There's a science magazine that did a piece on that. I have this link here if you want to go and dig further. They found this tablet. They call it tablet from the ancient time, and people were trying to look at the stars in the sky and so on. Okay, so it's amazing how this method went back thousands of years. What about Simpsons? 10 times better. Well, that's about 1700 something. Okay, now Simpson was a self-taught mathematician. This is amazing how he can be self-taught. Okay, now what about the quadrature? It turns out that a few, maybe 50 years later, you get this guy, okay, by the name of Carl Friedrich Gauss, who invented this method that is 100,000 times better than the ancient Babylonian. How's that for an improvement? By the way, okay, let's imagine that you are this guy, okay, that you are Mr. Gauss, and then you found a method that uses same computing power, but 100,000 times better. How do you publish a paper on that? How do you convince your friends and your peers that you have found that method? สมมติว่าคุณเป็นคนที่ชื่อเกาส์นะครับแล้วก็คุณไปเจอวิธีการที่จะอินทิเกรตให้มันได้100,000เท่าแม่นยำกว่าที่ผ่านมาเนี่ยคุณจะไปตีพิมพ์เปเปอร์ยังไงคือคุณจะพูดยังไงให้คนเขาสละเวลามาอ่านมานั่งอ่านนั่งดู proof ต่างๆเพราะว่าพวกนี้มันต้องใช้เวลาถูกไหมครับการที่จะมีคนมาเป็นผู้ทรงหรือว่าใครที่จะมารีวิวเปเปอร์คุณมันต้องเปิดอ่านมันต้องเช็คพิสูจน์ถูกไหมตัวอย่างใครก็จะมาเสียเวลานั่งดูงานของคุณถ้าเกิดคุณแบบบอกก็ตุ้มฉันทำวิจัยได้100,000 เท่าดีกว่างานของคนก่อนที่ผ่านมาส่วนใหญ่แล้วมันก็ยากมากนะครับนอกจากคิดแล้วยังยากด้วยการที่จะไปโน้มน้าวคนให้มาฟังเรายิ่งยากขึ้นไปอีกนะครับเพราะฉะนั้นคุณก็อย่าท้อแท้นะครับถ้าเกิดคุณมีของดีๆเจ๋งๆนะครับพยายามที่จะทำให้เต็มที่ในการที่จะทำให้คนเขาเสียเวลามาอ่านงานของคุณนะครับ and so that's the history of these methods. Well, if you understand the Gauss quadrature method and you did the homework problem correctly, then you have understood the secret of integration. And let's build on that. Now let's make a homemade quadrature. Okay, do our own version of quadrature. Now put your researcher hat on. Now you are a researcher and you want to invent some stuff, and you want to find your own way of integrating. What can you do? A homemade quadrature. Okay. Now let's define the problem. Okay, precisely. Okay. Suppose I have a function that goes from -1 to +1, and I want to use only 5 points, only 5 sampling points, and I label that point, that one at -2h, -h and 0 and so on. Okay. Now, for any function f of x, I can approximate the integration in that way. I can sample the function at the 5 points, the fxi, multiply to the weight wi. I should get the sum, and that summation should be equal or approximately equal to the integration of that function. Okay. Now, if you go back to the previous class, I give you here a review of the weight of this trapezoidal 1,000 years ago, or Simpsons. The weight is as shown here. Okay. Now, this thinking guy wants to know his own set of W. Can we come up with our own set of W and then use matrix and use vector to do the things for us? Can we do that? Okay. Now let's put that idea there. Now, of course, it's not going to be possible for this method to be exact for every function. That's not. Maybe it is possible. I don't know, because maybe in the future someone would find a way to compute only 5 sampling point, an exact answer for every function known to man. That maybe people always think of new things, but at this point in time, we don't know how to do that just yet for every function. But at least we can choose a set of function such that these are exact. And I chose 5 function here from polynomial basis. If it's 1, if it's x squared, and so on. Okay. Suppose you want to find the weight for this homemade quadrature such that these functions give you the exact answer. Now, let's go one by one for each function. If we have this first function, a constant with a 1 here, and I do integration, okay, and you can do this by hand, it's equal to 2 for that one. What about the next one? If f is an x, a simple x, I skip a step. Okay. If I do the quadrature, I simply sampling the function at this point, and that point, then multiply to my weight. It should be equal to number 2, because the condition is that we get the exact answer for this case. So it should be equal to 2. Now, if I sample this function f, what do I get? I get 1, 1, 1, 1, 1. Why? Because my function is just in one constant for this case, for this first case. So I have that equation here in the green box. What about the next case? If my function is x, just x, and I go online and use my Wolfram account to do integration, I get 0, okay, because it is symmetric and negative and positive. I get 0 for this case. I begin then again write down the form of quadrature. I sample these points and then multiply to the weight. It should be 0 Why? Because the exact answer is 0 for this case. Now, when I sample this f1 function, what do I get? At 0, I get 0 because this is my function. What about at 2h? I get back to h because my function is a simple x function. You have minus here because when x is minus, so is the f, the same sign over here. So I have that equation here. Now, before I go on, I can do some manipulation, just to make it simple. I can divide the h. I can divide both sides by the h number. Now, when I do that, I get 0 on the right hand side. When you divide both sides by h, you have 0 here. What about on the left hand side? The h goes away. We only have the 2, minus 2, minus 1, and so on. Okay, left. Why do I do that? Because I want the left hand side to be simple in this case. Now, the next case, which I'm going to go faster because now you get the idea of how you do that. The exact calculation is 2/3 for this x squared. And when I do the same method, I get back this equation. In here I have h squared because I have to divide the whole thing by h squared in this case. Remember, we have x squared here. The next case and the next case. Okay, so we have constructed 5 equations, and then we want to solve for 5 unknown. How do we do that? How do we do that? Let me leave this question here. How do we do that? Any idea? From a homemade quadrature, we have built ourselves these 5 functions. And by the way, h is 1/2. You can put 1/2 there for h. What should we do next? Any idea?
Yes.
Oh, Dishan, I haven't heard from Dishan. Yes.
Can we use Gaussian elimination?
Okay, but before we do that, before we do the Gaussian elimination, can we make the problem looks nicer?
Oh, we can write it in the. We can write it in the form of argument matrix.
Very good. Okay, we can do it in a matrix form, if I heard correctly, like so. Very nice. Now it's very simple. And with here we have 5 unknowns. We have W0, 1, 2, 4, and you have that matrix, which is a constant, and you have this on the right hand side. You have a constant, and h is 1/2, and you can solve for the unknowns for a homemade quadrature. And how do we do that? Okay, my mouse. Okay. Well, we have that linear problem. Okay, the M is the matrix, W is the unknown, and B is the constant on the right hand side. Find W. How do we find that? I can multiply an inverse of the M matrix to the left hand side, right there and right there. So this one, I get back identity matrix, that is W, and so I have that formula of solving for W. But the matrix M is very complicated. How do we find the inverse of a matrix? I always use in my research career, I always use my tools, okay? And I have here as an example for you, you can use Wolfram Alpha. You can put any matrix you like, and you get back all kinds of information about the matrix. Let's do that here. Live in where's my matrix? It's my homemade quadrature. No, there you go. I can copy this link, okay, which I put online, and then put in let me erase there. It will be in the Wolfram Alpha website, And let me reduce the size of the view here. I just simply put the matrix there, and it show me that this is your matrix. 1, 1, 1, 1, 1, and so on. The same as in the PowerPoint. Like there. Okay, so I go back to here. It tells me it's 5 by 5, the dimension, the color, determinant, and the inverse. Very good. Now we know the inverse. Now we know the inverse of this matrix. We simply just multiply that inverse to the B vector, and you get back the W. Okay, very simple. Okay, or you can use Python. You can use Fortran to do the things, but I like to use Wolfram Alpha because it's free and it's very good. Now, what's the next step? And finally, our homemade quadrature is now that here. Okay, I do that. I get that answer. It's kind of very strange, but I put that in here. Let's do how we did. Okay. If I do the same integration, I compute the error of this method. I get that here. It's not as good as the Gauss quadrature, but at least it's better than Simpson's method. Okay, it's an improvement from a Simpson's method. But here, for if f is the polynomial, you get perfect answer, 0 error. If f is a polynomial, you get also perfect answer, 0 error for our homemade quadrature. And so we have successfully, built our homemade quadrature. Now, how do we make it better? Any idea? Oh, by the way, I found a way to plot quadrature sampling point, which I found that method from Chanita's homework solution, and was very good. Now she showed in her homework solution how to use the shaded color to show you the sampling point of these quadrature. If you have a simple trapezoidal and Simpson's rule, the spacing between each sampling point is equal. It's evenly spaced, okay? However, for the Gauss quadrature, you have that uneven sampling point, somewhat smaller on the edges and bigger in the middle. Okay, that's how Gauss was designed. So you can imagine that you can make this one better by doing what? Any idea? By changing what of the quadrature? Because here we have the sampling point that we are using in the homemade quadrature is still the same evenly spaced edge. But if we do something, differently, we may get a better answer. What is that? How would we make it better? จะทำยังไงให้มันแม่นยำขึ้นมีวิธีการปรับhomemade quadrature ของเราหรือเปล่าเอ่ยมีไอเดียไหมเอ่ยเราอาจจะไปเปลี่ยนตรงไหนของมันเอ่ยลองถามคุณชนิดาพายและคนที่ออกแบบคุณแพนด้าคนที่ออกแบบการโชว์รูปภาพแบบนี้นะครับมันต่างกันยังไงระหว่าง homemade quadrature ของเรากับกรณีของGauss quadrature
ระยะห่าง
ตรงจุดที่เราแซมเปิลฟังก์ชันใช่ไหมครับหรือจุด abscissat ถ้าเราเปลี่ยนจุด abscissat อาจจะทำให้มันแม่นยำมากขึ้นนะครับ อาจจะมากเกินของเกาส์เลยก็ได้นะครับอาจจะกลายเป็นแบบว่าซูเปอร์สุดยอดซึ่งใครจะไปรู้นะครับก็ต้องหวังพึ่งคนสมัยใหม่ให้มาคิดต่อยอดนะครับไปเรื่อยๆนะครับก็ตัวอย่าง
อาจารย์ครับ I have a question ครับ because of over here you start with all like polynomial functions, right? For example, if you start with something different, like for example, if I start with like sine function and mix with
very good
polynomial function, is that better? I mean,
okay. So you're asking the set. Oh.
Yeah, the starting set of the quadrature.
The set of quadrature which we choose to be exact. That can change. Oh, okay. I guess we have problem. My neighbor is using lawnmower. Let me see if I can close my window. Very good. I hope it's better. Is it better with the background noise?
อยากจะดังกว่าเดิมนะคะ
Yes. Is it loud?
เงียบไปแล้ว
How am I supposed to do this? I cannot stop the background noise from coming in at all. Even I'm talking here, I can't hear myself. Okay. What should we do? Damn it. Okay. To answer the question, yes, we can change the set of function which we choose to be exact, and then you're gonna get different kind of quadrature. If I may go back to the Google and Wikipedia quadrature integration, and you will see a whole list of recipes for the quadrature, and each will have different set of the exact function. Let me go see here. We have other form. There you go. You have Lagrange polynomial. You have Jacobi polynomial. You have Chebyshev and Hermite polynomial. All kinds of strange function that you choose to be exact. Okay, and that will give you some different accuracy for different kind of applications which you can choose. Okay, let me give you where's that sine and cosine. Control F, sine function. No. Okay, where's sines of x? I forgot. There is one quadrature made for sinusoidal function. I forgot the name of that quadrature. The name is somewhere in here, in the beginning of the here. Oh, I forgot. I'm sorry, I forgot. But there is one quadrature for sine and cosine function, and that will be very good for if you integrate like periodic function. Okay. Now, before I go on, how are we doing with the background lawnmower noise? Can you on the other side hear the noise?
We can
Yes or
hear,
no?
but not that bad. Meaning we can hear Ajahn very clearly.
You can hear the noise, but not that bad. Is that what you're saying?
Yes, yes,
Is it
Ajahn.
bad or is it good? Because I already closed the windows, but I guess I cannot make it any better at all. So I'm wondering if I should stop the lecture now and continue in the next class. What do you think?
There's not much disturbance, Ajahn. We can hear you.
Okay. Okay. If that's the case, then let's continue to. Did did I answer the question for you?
Yes, thanks.
Okay, thank you. That's it. For the questions, I need to upload. Okay. Now let's go. I need to go back a little bit here. Okay. So let's go to the next topic of this kung fu exercises of how you visualize things in matrix and vector form. Okay, we did that with the quadrature. Now let's go to what we call eigenvalue problem. Okay, what I have here is the typical example of matrix and vector multiplication. If we have some vector, you multiply that to a metric, you're gonna get some another vector like so. But suppose we have a very special cases, very extremely rare cases of vector. For example, if I multiply this special -1, 0, 1 to this same matrix as before, what do I get as a result? Oh, I get back the same vector as before. So this is a very special case of vector, and we call that eigenvector. Let me give you another example. If I have another vector, let's say 0, 1, 0, I multiply that to this matrix. And what do I get? I get kind of different vector. But no, if I factor out number 3, I get back the same. Vector. So this is what we call Eigen problem. We want to find a vector that if multiplied to this metric, you get back the same vector as before. Of course, with some pre-constant in the front. Okay, so that is what we call Eigen problem. How do we find these special cases? Okay, well, the answer is you use software package, you use Python code, you use Wolfram Alpha, and so on. Okay, that is the official writing of this problem. We have matrix M. You want to find a vector A. If multiplied to M, you get back the same vector with a pre-constant in the front. Okay. Another aspect of this Eigen problem is that if you look at the vector in terms of direction, okay, suppose I have a 2 by 2 matrix A, and then I multiply this as some vector 1, 1, I get back another vector 4, 7. And if you look at the direction of this before and after, you have two pointing vector. Okay, so that is a simple vector. But if you have an eigenvector, you see what happens. 2, 1, you get back the same, and the answer will be in the same direction as before, but 5 times longer than before. So this is a property of a vector problem. It preserves the direction of the vector after multiplication. Okay. Now, before we go on to the exercises, we have one last aspect of the vector, of eigenvector. Suppose I have an eigenvector, let's say 2, 1. Of course, if you multiply them, you get the same back, 2, 1, with the phi being the eigenvalue. Okay. And then I multiply number 3 to this original vector, what do I get? I get now 6, 3. See, 3a. Now, is this still an eigenvector? The answer is yes. Okay, if I do multiplication, I get 30 and 15. I can factor out number 5. I get back the same vector. So what is this? Is that if we have a vector A, multiply this by a constant, you get the same eigenvector. But it could be longer or shorter, it's just the same. The direction is preserved. Okay. So let's go to the exercise of this here. Okay. Before you go on, I have some quiz just to check if you understand the concept of complexities here. Let's ask Patrada. Okay. Suppose I have a matrix, and of course the function of complexity is n to the n cube over here. Suppose I double the size of my matrix. It's going to take longer to compute. How many times longer? Suppose I double the size of my matrix. It's going to take longer to compute, but how many times longer? Just put my earphone in there.
โอ้นานมากๆค่ะแต่ว่า
But
2 เท่า
give me an estimation, because the complexity function is n cubed, but n is the size of the matrix. Suppose I double n is 2 times bigger. The computing power cost will be how many times bigger? Remember n cube. Suppose
เป็น n กำลัง 6 นะคะ
suppose let's see. So the cost is n to the 3rd power. Let's give an example. Suppose n is 1. Suppose n is 1. 1 to the 3rd power is 1, right? Now suppose we double the size of the problem. Let's make it 2. Now n is 2. What do you think is the O function?
8
So that means the computing power is 8 times bigger than the previous problem. And that's how it's difficult to keep increasing the size of the matrix, because at some point you get this limitation of your computing power. Okay, if you make the matrix 3 times bigger, how much longer do you wait? Only 3 times bigger, but you have to wait longer by how many times? Let's ask Patrada. What do you think?
ช่วยแปลคำถามได้ไหมคะยังงงอยู่เลย
สมมติว่าคุณเนื่องจากฟังก์ชันของการคำนวณมันเป็น n ยกกำลัง 3 สมมติว่าทำโจทย์ให้เม็ดของคุณมันขนาดใหญ่ขึ้น 3 เท่า คุณต้องใช้เวลารอนานเพิ่มขึ้นกี่เท่า?
โอ้ก็24เนี่ยเหรอคะเดี๋ยวนะ3แต่ว่า8เท่า3กำลัง 3ก็9เป็นเดี๋ยว n กำลัง 3เดี๋ยว3กำลัง 3เท่าไหร่ไม่ใช่27ค่ะรอเสียงเปิด27เท่านะครับอันนี้คือน่าจะดูซีรีส์นานเกินไปยังไม่ได้นอนนะครับ
ใช่
ใช่ค่ะคือกำลังงงว่าที่เป็นยกตัวอย่างคือ n เท่ากับ1 n เท่ากับ2 n เท่ากับ3เนี้ยเหรอคะที่บอกว่าไซส์
oh Ron towards 8 times longer correct let me give an applause okay very good n นี่ก็คือขนาด n นี่คือขนาดของเมตริกที่เรากำลังแก้โจทย์อยู่นะครับถ้าขนาดมันใหญ่ขึ้นมันก็จะไปยกกำลัง3นะครับเช่นถ้า n มันเป็นเพิ่มขึ้น2เท่าก็จะต้องเป็น2กำลัง3ก็จะเป็น8นะครับรอถึง8เท่าถ้าคุณบอกว่าคุณต้องการที่จะแก้โจทย์นี้โดยให้เมตริกมันเพิ่มขึ้น10เท่ามันจะต้องรอนานขึ้นกี่เท่า
ก็10กำลัง3
ก็เป็น1,000เท่านะครับ1,000เท่าเนี่ยมันรอไม่ได้แล้วนะครับถ้าสมมติว่าคุณนั่งรอเครื่องคอมคุณรัน1วันเต็มๆถ้า1,000เท่าเนี่ยก็3ปีแล้วนะครับมันก็จะกลายเป็นว่ามันคำนวณไม่จบสักทีนะครับเนาะso that is the review of the basic okay now I need to go and take a break in the restroom a little bit let me put the waiting music on and let me take a just brief break to a restroom and I'll get back now what is the time now back at 14 point let's take 35 okay restroom okay very good be back in a few Oh, the lawnmower is getting farther away, so it's getting better with the noise. We still have 5 minutes to before we officially get back with the class. Okay, so let's enjoy the conversation with the people. Okay, let's see. We have still we have 5. Very good. You know, if you have friends who would benefit from this lecture online on YouTube video, just feel free to tell them the link. Okay. Let's get back to this here. The research. ลองหาเวลาสร้าง Quadrature ดูนะครับถ้าคุณมีเวลาว่างที่มันแบบมันแม่นยำใช้แค่5จุดแล้วมันแม่นยำกับทุกฟังก์ชันที่เรารู้จักในสากลโลกนะครับมันอาจจะมีสามารถทำได้นะครับผมไม่รู้มันเป็นเรื่องของการใช้กลืนแล้วก็ชาวปัญญาคุณลองดูขนาดแม่นยำขึ้น 100,000 เท่าถ้าเริ่มนับจากทรัปซอยโดนะครับมันยังทำได้นะครับใช้5จุดเท่าเดิมครับซึ่งผมลองเดาได้เลยว่าถ้าคุณเป็นมิสเตอร์คาวคุณไปตีพิมพ์เนี่ยจะมีฝ่ายค้านเยอะมากนะครับก็จะมีคนมาค้านว่ามันเป็นไปไม่ได้หรอกก็ใช้5จุดเท่าเดิมมันจะไปแม่นยำขึ้นได้ยังไงนะครับมันต้องใช้จุดเยอะขึ้นนะครับก็ว่าไปนะครับคือปกติแล้วเขาก็ไม่อ่านก็คือไม่เสียเวลามานั่งอ่านก็โยนทิ้งลงถังขยะโอเค
แล้วเราทำไงให้เขามาอ่านนะคะ
เราก็ส่งไปเจอหน้าอื่นแล้วก็ส่งเจอหน้าอื่นแล้วก็อาจจะคือมันยากพูดจากประสบการณ์ตรงการที่เราจะไปเจอสิ่งที่มันเจ๋งๆแล้วก็นี่ว่ายากแล้วจะโน้มน้าวให้คนอื่นเขาเชื่อได้ว่ามันเจ๋งจริงอย่างที่เราบอกเนี่ยมันยิ่งยากไปอีกเพราะหนึ่งเขาไม่ใช่คนที่จะมีเวลามานั่งคอยอ่านให้เรานะครับมันต้องอาศัยเวลาต้องอาศัยทรัพยากรถ้าเกิดเขามองว่ามันเป็นไปได้ยากไม่คุ้มค่าเสียเวลาเขามันก็จบตรงนั้นแหละนะครับก็อย่าท้อถอยนะครับทุกอย่างเป็นไปได้เสมอนะครับ100,000 เท่าใช้แค่5จุดยังเป็นไปได้มาแล้วนะครับคุณก็อาจจะคิดที่มันเจ๋งๆมากขึ้นไปกว่านี้ก็ได้นะครับมีไม่เอ่ยมีใครมีเพื่อนเป็นที่อยู่เป็นอะไรชาวอเมริกันเป็นชาวอังกฤษนะครับร้อยเข้ามาฟังดูครับเผื่อเขาจะทำแต้มได้ A ในวิชาของเขานะครับโอเค I need some time with Agnesแล้วก็เรื่องของการใช้ complex number นะครับการใช้เมตริกขนาด2 คูณ 2เนี่ยมาแทน complex number นะครับทำให้สมบัติทางคณิตศาสตร์มันพอจะใช้แทนจำนวนเชิงซ้อนได้นะครับมันก็อาจจะทำให้เราสามารถรวมเอาแรงโน้มถ่วงทฤษฎีของไอน์สไตน์เข้ากับทฤษฎีควอนตัมของชโรดิงเกอร์ได้นะครับก็ทำให้คุณสามารถจะมีสมการหนึ่งเดียวของจักรวาลที่อธิบายทุกอย่างได้ทั้งหมดลองไปคิดเล่นๆดูถ้าเกิดมีเวลานะครับโอเค so we are getting back to the exercise of how we can use matrix and vector to solve problems again the equation is not important. What important is the skills of how you visualize the problem in matrix form. Now let's go to quantum mechanics. Okay, the Schrodinger equation. Okay, in this exercise, in this study, a case study, we are going to practice how to turn a calculus equation into matrix form. How do we do that? Okay, and we can do this what we call an electron in a bumpy box. What does it mean? A box here is not flat, but it's bumpy. Okay, it has dips and holes and so on. So the potential function of that box is described by a function v sub x over here. And the box begins from x equal to 0 and x equal to L on the right edge of the box. So we would begin with this simple Schrodinger equation in one dimension, like in this shown here. Usually, when we do research about quantum mechanics, we don't keep track of all the h bar constant or all the things. It's too complicated. So we use another set of unit instead. And in this unit, we have a special selection of the number such that the h bar is 1. And the mass of the electron is also 1. And the charge of the electron is also 1 unit. And so with this convenient unit, we can do a lot of, we can simplify a lot of math equation. For example, the equation becomes that here. The h bar goes away because it's just a number 1. The mass of the electron goes away because you only have this number 1 here. We have much simpler equation to work with. Okay, so learn how to use that unit here in your research. If you do material science, if you do quantum physics, they usually atomic units here. So we want to solve this differential equation in eigen form. Okay, we need to have also what we call boundary condition. What is that? Is the behavior of the physics on the left and on the right boundary of the box. The physics of this is the following. Because the function psi here in the math means the chance of finding the electrons at certain location. So therefore, because the box is very rigid on the left and on the right, you cannot have any electron outside the box. What that means is that the function needs to be 0 here on the left, and on the right here should be 0. So that is what we call the boundary condition of this problem. For other problems, you have other kinds of conditions, but for this case, we have that condition here. So how do we find, in this case, a solution of the problem? Input is the function of Vx, how bumpy the box is. And we are going to solve for the energy of the electron and the wave function of the electron. Now, if you do not know quantum mechanics, that's okay. It's perfectly fine. Think of this as just a mathematical equation. In this math equation, you have that equation here. You have this unknown psi and unknown E. And how do we find it? Okay, but if you by any chance want to learn more about quantum mechanics, now is your chance to learn more. You can go online and look at this very nice video from Dr. Chachiyo. Let me take a break a little bit and advertise things here. If you go to the website, for example, and you click on the menu bar, you click quantum mechanics there. There you go. Have a bunch of book and lecture video over there. That was me 10 years ago. All young and handsome. Okay. Now, in this class, has anyone seen my quantum lecture before? Let's ask the audience in the hall. It's given in Thai, of course, but has any of you seen this video before?
I watched two, which had a English subtitle.
Okay, there's an English subtitle from my assistant. What about the Thai students? Any of you took the time to listen to this great lecture of the time? What?
ฟัง
No.
บางคลิปแล้วค่ะ
A little bit. Well, you should watch the video for the entirety. You know, it's like think of it as a great series, a movie series like Bao Bunjin. So let's get back to the material. So we have that equation. You want to find the solution of the function psi n, but this is still a calculus form. Okay, how do we transform this into matrix and vector? Okay, that's the lessons of this lecture. We begin with the same equation, and we can go back to what we had before in the previous lecture, the finite difference. In here, we can make a sampling point with even spacing, and the distance of that spacing is h value. We can compute the derivative of the function, first derivative, second derivative, using that formula here. Now, how do we use that formula and to solve this PDE? Okay, and here I have the space in one dimension. The black dots are the condition, the boundary condition point, and we know that the answer is 0 for these two black dots here. We know that already, and the unknowns are shown in blue. Okay, we want to find the psi value for these blue dots here, and the spacing is the h. Now we label the dots 0, 1, 2, 3, 4, and so on. Okay, now let's look at some dot in the middle, in between. Let's call that dot I, and the one on the left I minus 1, and the one on the right is I plus 1. So let's look at 3 dots here. Okay, now we have that math equation, and then we can transform that math equation into finite different form using that formula here. You see there, I can convert this derivative into this one, still keep the minus and minus, 1/2 still there, 1/2 still there. That's the first term. The second term is still vi at that point, at that I point, times psi I at that point equal to constant and psi I. So we have that equation. We can do further. We can rearrange the term, you know, massaging the mathematic formula. You know, make it more convenient. So how do we do that? How do we massage นวดสมการให้มันเข้าคลึงกลมกลืนกันสวยงาม How do we do that? We can multiply both sides by the h square constant. Let's see, how do we do that? If we do that, there you go. On the right hand side, we have now h square. But look, now this one's gone. See, because we multiply by h square. So it cancels with the denominator here of that one here. So and I can, you know, try to put some color. Okay, now put some color into this math formula. I can paint the unknown function with the blue color. That's my blue color. Psi I minus 1, psi I minus 1, psi I here. Let's. By the way, in my research career, when I do my research, I always paint my equation with color so I can see the pattern better. See in my research. So what do we do next? Okay, I have painted the unknown with the blue color. Okay, dot here, and I also painted the coefficient with the red color here. We have minus 1/2 multiplying to psi on the left, we have -1/2 to the psi on the right, and so on. Okay. Now, what's the next stage? Let's focus our attention at the first point in the label, the I0. Okay. So what do? Now, if you look at this pattern here, you always have 3 points. 3 points. The one in the middle, the one on the left, and the one on the right. On the left, you always have to multiply -1/2 on the left. On the right, stay -1/2. In the middle, you have that something there. So let's focus in this 0 point. Okay. So can we write an equation for this 0 point? Yes, we can. You see there? We have the point in the middle, that term. We have the point on the right, -1/2 psi 1. Why don't we have the point on the left? Let's ask Patrada, because she's an expert in solving this equation. In fact, I know that it is her thesis when she was working in a degree last year. So why don't we have the point on the left?
Because wave function equal to 0 at the boundary.
Very good. There you go. Okay. Let me give you an applause there, and also the bell. Okay, the bell. Very good. Thank you. We actually have the point on the left. Yes, we do have it, but it is 0. So 0 multiplied -1/2 is 0. Okay, it's over there. So we only have that here. What about if we move the attention, move the focus to the right a little bit, to the point number 1. Okay, now we have the I is number 1, and the left is 0, and the right is number 2. Can we write down the equation for this point? Yes, we can. We have that. Now we have all 3 points. Point in the middle, on the left, and on the right. Again, I'm still painting the coefficient with the red color there. I move on further to the next dot, the next point, point number 2. Can we write down the equation for this 3 points? Yes, we can. We have that over here. Now, look at the pattern here. We have an equation on the right, the same constant, h squared e, multiplied by the corresponding point, psi 0, psi 1, and psi 2. The last step is that we have to realize this equation in a matrix form. How do we do that? That's how we do it. You just rearrange the term in matrix. Now, you would, okay. Now, let me ask a question. Di-Chen, do you think the way I paint the color into the equation, is it helpful?
Yes, Ajahn. So the matrix becomes very clear.
Very good. Right? With the color, you can see it better, the pattern of the mathematics. Now, this is what I use all the time in my research. Okay, in my notebook, I always try to paint my notebook with color, with certain term. It's very fancy. It's not just what I do in my lecture, but also what I do in my real life research. Okay, so I see the pattern much better. Okay, now I can then transform this equation into the pattern. Look at this pattern. This is what we call a banded matrix. What does it mean? A banded matrix. It means that the matrix that has only a certain value in the diagonal over here. The rest are 0. Okay. In this case, the diagonal values will be 1 plus h squared v0 and minus 0.5 minus 1/2 on the left and on the right. So we have this matrix, and we can ask software package to solve for the eigenvector and eigenvalue for these. Very simple. But then we have to think of the problem in terms of the matrix first. So we have that final version of the matrix form of the PDE. See, in conclusion, what we have done, we have transformed Schrodinger equation, which is a calculus equation, into a matrix form, like so. And we have to build this matrix and then ask the program to solve the eigenvalue, which we're going to get the energy, and the eigenvector, which we're going to get the wave function cosine for us. Okay, now so let's go to the Python code to get a big surprise in the result. Okay, again, you simply go to the class website, mathematical method for physics, and then click on the matrix, linear, inverse, and eigen. Okay, click that. You go to this Google collaboration. Okay, now I have here a simple, brief review of what we are doing. We begin with Schrodinger equation. We then use what we call atomic unit with h bar, mass of the electron, and the charge of that is equal to 1. So we have a simple equation like that. Okay. Now, we have to decide how many points do we need to solve the problem. Luckily, I make a very nice code in Google Colab. If you click there to compute the Python code, in this special code, you can actually select from a sliding bar the end point that you need or you want for your solution. Let's say I want only 5 points. So we have 5 blue unknown, 1, 2, 3, 4, 5. Now from that, you can see that the h will be L, the whole length of the distance, divided by how many interval? 1, 2, 3, 4, 5, 6. That's for the h. L divided by n plus 1. Okay, say we have 3 points. Then you have 1, 2, 3, 4 region. L over n plus 1 region. Anyway, I can choose like let's say numbers. What is your lucky number? What is Panda's lucky number? Which one do you like?
12.
Okay, let's go with 12. Okay, 12 points in. Once we have that 12 points, I can then use my Kung Fu. I can use my Python Kung Fu that I have trained, that I have been trained for 30 years to compute my A matrix. You see there, that's my A matrix. You know, the diagonal is just 1. Why? Because in this problem, I want to explore a very simple box, which we call a particle in the box. You can check that online. See that I can, maybe you can trust Wikipedia. Say particle in a box. You know, a very famous and popular problem in quantum mechanics. The box is flat, so the V is 0 in the middle. Okay, if the V is 0, therefore we only have number 1 here. Okay, because the V is 0. So we begin with that simple problem, and we're gonna build on top of that a bumpy box. Let's say we have the simple particle in the flat box instead in the beginning. So we have that A matrix, and once I have that A matrix, I can use what we call Numpy. Numpy. Has anyone used that Numpy before? What about Panda? You know a lot about Python code. Have you used Numpy before?
Yes.
Okay, very good. Now I have a big surprise for you. Okay, if you go to Numpy documentation, you can always check online. I do this all the time. I go to Google, I type Numpy, and I type Eigenvalue. I just want to see what is the command or what is the function that I can use to compute eigenvalue and so forth. I do that, and I put the code in here. The function is IH, the some name for eigenfunction. So I click on that. I click on that to compute my eigenvalue, and I get that result, okay, over here, energy. I want to check if I get the right answer. I can go to some textbook, or in this case, Wikipedia. I can look at the energy value for this here, and then copy that code into my notebook. I print this out here. That's the exact answer for this problem. Only when you have flat box, okay? Look at the agreement. We have 1.227 for the our result, and the exact is 1.23. Very good. What about the next one? 4.8, 4.9. Very good. So it seems like we're getting the right answer for this problem, okay? What about the eigenvector? If you go back to the formalism that I have here, when you solve the eigenvalue, the lambda, you get the energy, okay? The eigenvector in blue is the point of psi, is the psi for every point. If you plot the graph, you're gonna get the answer. Let's go to see what we have here, okay, and get the big surprise. If I take the eigenvector, the first eigenvector, and plot the graph, I get this graph here in blue, okay? That's from Numpy. The graph seems very odd. It goes zigzag. It goes zigzag with this here. The sign go from plus to minus and to plus again. It's kind of very strange. Now, if I fix this problem by taking the absolute value of the Numpy answer, I get this nice curve there in light blue, okay? So there's something wrong about this subroutine in Numpy of how you get the eigenvector. For eigenvalue, it's okay. It's okay. I dig online. I check online, and there is this information about there is a bug in the Python code, okay, of how you can compute, and that is in January of this year, okay. So what is the lesson that you learned in this exercises? Is that, well, you always have to check your answer against some known solution, because things can go wrong. You can make a mistake in your code, and even if you did it correctly, there's still some bug in the Python code. So it's very strange how I found this here. Now, because there's a bug in the Python code, maybe we need to use another tool, and that is why I prepare my Octave. Let's see, I have written another code in Octave, and let's see if Octave give me the right answer. Okay, let me see there. Octave finish. I just install Octave in the beginning of this lecture, and let's see. Next, and then finish. This is an Octave program. It's the same as MATLAB, more or less, most of the time. And and I know how to do programming in Python, MATLAB, Octave, MATCAT. I know how to do it in C, in C++, in Fortran. I know all kinds of programming because I have a lot of kung fu power. Anyway, let's go to my Octave source code. Now, if you don't know how to do Octave or MATLAB, it's fine. I just want to show you the variety of all the things that you can learn in your childhood. Let's see, go to documentation and notes, my Octave. Where's my quantum bumpy box? Oh, very good. Now I can double click. Here is my code. Now I'm not sure if you can see the code because I can zoom in. Very good. I'll put this code in the website. Anyway, it's the same concept as before. You know, you define your the n, define the length of the box, and then you build your matrix. Let's run the code. Let's say I use the 12 as before. I run the code, and I have that command here. That is 12 is too big. I can't see the matrix. Let me change it to some smaller number. Let's make it only 5 points. Okay, 5 points. There you go. And I look at these windows. Let's make. Why is it? ELS. Clear the screen because there's so many junk on here, and I click. Oh, okay. I'm not. Okay, I forgot. I need to change it to a simple flat box. Okay, let me do it again. There you go. That is my. If you can see it, the matrix A. Okay, that is my matrix A. There you go. 1, 1, 1, 1, 1, and the minus 0.5, 0.5. That's my matrix A, and then I compute the energy value, and then I just get the wave function. Once I plot the wave function in Octave, where is that? Now, there you go. I can, maybe it's difficult to see. I have two functions plotted here. I have the calculated value for the 5 points in blue, and I have the exact answer in brown over here. So they're in perfect agreement with each other. I can instead change the size of the box to make it bigger. Let's say 15, 12, and run it again, and I can see the code. See, perfect answer between the computed value from our program and the exact answer for the flat box. Now I can see how the electrons are doing. This one is I am plotting the potential function in the flat box over here. And this is the wave function that I get. Now, most of the electrons are in the middle of the graph. You have this maximum here because the box is flat, and therefore the particle stays in the middle usually. Now, if I make the box bumpy, for example, I can go back to my Octave code and then change the potential function from a flat 0 to a bumpy curve. Let's see, right there, and I do the same calculation again. Okay, here's my bumpy box. The box has a sinkhole on the right, so potential is huge on the left part, and on the right part is steep downward. So the particle from the calculation stays at the bottom of the box on the right here. Okay, it's just like what we have here. So this is how we compute the Schrodinger equation for all kinds of potential. You can use this code to design semiconductors, to design your machines, your devices at the nano scale, and so forth. Okay, but that is not the main concern of this exercise. The concern is that we need to know two things. first is you need to know how to visualize this PDE equation in matrix form. And secondly, you need to be aware that all the Python code or C code or anything that's machine can make error, and you need to check your problem very systematically, okay, to see if there's a problem in your machine or in your calculation, okay. So that should conclude the end of the this problem of matrix. Now we are going to we have one more topic left, okay. It's called optimization, and we're going to use what we call quasi-Newton method to practice the skills. The skill is how to visualize the problem in matrix form, but that should be let's put that into the next lecture, along with very exciting on request topics, namely the Navier-Stokes Equation. Okay, I forgot who made the request last week. Was it Dewey or is it Tosapon? I forgot who that was from. The guy from Japan. Okay, maybe he's not with us here. Maybe he's not hearing us very well. Okay, so any before we take off today, any questions so far that you want to add, or maybe I missed some point that you want to know more and learn more about some topic, and just make a request over here. And I know Ron cannot put the mic on, and so he had to type the answer through the chat message. And I hope that by the time you get to the end of this lecture, you have a better feeling of how you should transform your equation, your calculus equation, into matrix form. And what other technique that you do that you can use color techniques to make you see the pattern better, just like what I do in the lecture. And then you can use software packages like Numpy, Python, or C, Octave to do the computing for you. Okay. Any question before we take off today? Anyone or any comments? If you don't have a comment, I have a question for you, which I'm very confused about this behavior of the audience here. See, when I go online to my YouTube video, like here, I can kind of check the statistics of the YouTube lectures that I put online, like I'm showing you here. And when I do that, and it's very strange for me that out of the 5 videos, the video number 5 is the most popular, about the numerical differentiation, which is not the case usually. Usually we have number 1 is the most viewed, but in this case, number 5 is the most viewed. So I'm wondering if there is an explanation of why that's the case. Maybe number 5 is a lot more fun than number 1. What do you think? ปกติพอผมมาดู statistic จะเห็นว่าทั้ง5วิดีโอที่เอาขึ้นไปไอเบอร์5มันมีคนมาตื่นเต้นสนใจเกือบจะแซงเบอร์1ทั้งที่ปกติแล้วเวลาที่เราเป็นชุดวิดีโอขึ้นไปเนี่ยเบอร์1ที่เราขึ้นอันแรกเนี่ยจะมีคนมาดูเยอะสุดแล้วมันก็จะแผ่วลงครับเหลือ0ปกติแต่อันนี้มันกระโดดขึ้นมาที่เลข5นะครับเบอร์5ที่เราเรียนไปคาบที่แล้วก็เลยอยากถามว่ามันมีอะไรเด่น ที่มันสนุกหรือว่าดีกว่าเบอร์อื่นๆของเลคเชอร์อันที่5มีไอเดียไหมผมจะได้เอาไปเป็นกลเม็ดในการปรับให้มันน่าสนใจมากขึ้น
หนูคิดว่าเป็นเพราะว่ามันอัปเดตล่าสุดนะคะแบบว่าหนูเข้า YouTube แล้วหนูติดตามช่องอาจารย์ไว้มันก็ขึ้นช่องที่5ก่อน
เอาเหรอโอเคก็จะเป็นอย่างนั้นนะครับถ้าอย่างนั้นก็แสดงว่าทำมาดีทั้งหมดแล้วนะครับโอเคแล้วคุณพัฒดามีคำถามอะไรไม่เอ่ยส่วนไหนที่คุณงงที่สุดในบรรดาทั้ง3ท็อปิกที่เราพูดมาวันนี้นะครับและอันที่4นี่จะไปพูดในสัปดาห์หน้านะครับเรื่องของ
อ๋อค่ะเปล่าค่ะจะบอกว่าไม่มีค่ะเดี๋ยวกลับไปดูเลคเชอร์อีกที
ไม่มีปกติคุณไปดูซ้ำหรือเปล่าครับ
ดูซ้ำค่ะ
กี่รอบครับ
ถ้าหัวข้อไหนที่ไม่เข้าใจก็หลายรอบค่ะแต่ถ้าหัวข้อไหนที่บอกเข้าใจในห้องแล้วก็อาจจะรอบเดียว
โอ้แต่ว่าการดูซ้ำทำให้เราเก็บได้ทุกๆเม็ดทุกๆดอก
ใช่ค่ะประมาณนั้น
โอเคดีครับดีก็ถ้าเกิดยังไม่มีคำถามในตอนนี้นะครับ if there is no other questions I'll see you next week okay with very advanced Navier-Stokes equation and wave equation with the numeric PDE and ODE okay today I'm happy that you are with me today let's see we have theme song okay I'll see you next week
Okay. Bye. ขอบคุณครับ
ขอบคุณค่ะ
สวัสดีค่ะขอบคุณค่ะ
สวัสดีครับ